Hello and welcome to my class. I'm Grolin Annalisi from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. What's a PP account is? +6 5834444290. Today's topic is STP, DHCP, CDP, and ACL. In the last class, we said something about part of STP. Let's do a review first. We said it before. In the network, if all devices use a single device, then the single line is connected to another device. You will find it creates a single point of failure problem, whether it is a line or a device. We cannot allow nodes in the network to have a single point of failure, especially the core nodes of the core equipment. So we often have to analyze the entire network topology. There are some redundant devices and lines present. Then once a redundant line or device is generated, may cause loop problems. So we need to be in the second layer network environment to run protocols like STP. Let it help us break the loop in the network. Please pay attention. We talked about TTL before. In fact, TTL is a means to prevent loops. But it can't break. STP can break the network loop. Run a protocol like this. There are no loops in the network. This is the basic role and characteristics of the STP protocol. So what kind of method does it use to break the loop? It is a vertical structure, starting from a tree root and spreading branches upwards. Then it walks up to a certain device. Is there not going to be a single line plugged back into the original first device? This is not going to happen. It is acyclic. The way it passes is block some ports in the entire network. Keep them logically blocked. Do not forward user traffic. Then it can lead to no way to generate this loop. Or in other words, it is eliminated after it is generated. And if something goes wrong in the future network, for example, maybe a line is broken, I can make another interface open automatically. Complete the normal forwarding. So the agreement itself is pretty good. Today, we will formally talk about the specific content of this agreement. We talked about BPDU in the last class. In the STP of our NA stage study, there are two types of BPDU messages. A configuration BPDU. What is written in the PPT now is to configure the BPDU. The message contains these parameters. There is another type of BPDU called TCN BPDU. Let's talk about configuring BPDU first. For the NA stage, STP actually involves little experimentation, because it learns its forwarding mechanism by default. So we are in the process of lecturing today. There will be more parameters to compare. So it might sound a little difficult to understand. Let's first talk about the parameters mentioned in the previous lesson. BPDU is called Bridge Protocol Data Unit. That is a message when all information in STP is interacting. This is the message form of their interaction. In the future, we are going to conduct some role elections. For example, I want to elect a root bridge, root port, specified port. You can see it here. They will compare the messages sent to each other. Let's look at this sentence. In the future, we will conduct role elections. Never mind what you choose. When we are doing role election, will depend on the path cost, peer bid, peer PID, local PID. Here are the parameters we compare today. These parameters are covered in this message. So after they send messages to each other, to determine the respective device and port status. That is, devices are updated through BPDU messages. This is part of what we talked about last class. In the last class, we first talked about RID. It's called the root ID. That is, root bridge ID. In this field, it is always filled with the ID of the root bridge. I will simply draw a picture here to explain. Let's take 3 devices as an example. This is 3 switches. They are sending messages to each other. The sent message looks like this. It's all here. Then in this message, this root ID is always the root bridge ID. For example, this is device A. This is device B. This is device C. Assume that device A is used as the root. Messages exchanged by all devices in the future. This is all A. Equivalent to. In order to ensure the stability of the topology as a whole, the root bridge will periodically send packets downward. Other devices will forward these messages. Then while they forward, we'll tell all devices that the current root is A. In order to ensure the stability of the topology. So this field is always filled with the root ID. There is a bridge ID behind. It is always filled here. The ID of the device that sent this message. I give a simple example. For example, now the first message is sent by device A. Then the field in the message it sends will be A. Then this field is also A. One means that device A now thinks that the root bridge in the entire environment is A. Another representative is that the device sending this message is A. When this packet arrives at device C, if there are devices below, if it wants to forward down, the root ID in device C is A. But here it will be changed to C. That is, it forwarded the message. Then it needs to change the bridge ID of the sending message to itself. Bid means that it will populate the device's own bid. Look down and there is a PID. It's simple. PID refers to a parameter in the interface, where the device is currently sending this message. The PID is calculated and generated by the priority of the interface plus the port number. So this PID is generated by the STP protocol. Don't worry about this. We're waiting while we do parameter comparisons. I will tell you about this PID again. Let's go back and talk about this root path cost. We didn't finish talking about this in the last class. Let's explain it next. For the current device, I will fill in the current distance of this device from the root bridge. That is, the distance between the device and the root switch. Then we're going to have a character election right now. First we will elect a root. A tree root selected by STP is actually a device. We call it root bridge, also called root switch. There is no distance between the root bridge and oneself in packets originating from the root bridge. Now overall this parameter is 0. There is no distance from this device to the root, because the root is itself. For example, now this is still a device like this. I'm connecting them now. It now sends out a message. Then the original RPC message is actually 0. When we calculate RPC, only the cost of the receiving port will be calculated. For example, the receiving port is now 1. Then when it receives the message, when it goes down, the RPC in this message will become 1. Then received by this interface, and then it sends down. We'll accumulate the RPC of this interface again. Further down, send out is 2. Then it is received by the next interface. This should have been mentioned when I talked about routing protocols before, such as calculating cost. We call the outgoing direction of the packet. If you send it here, it is this interface, or called the inbound direction of root convergence. Routing is reverse convergence like this. Then this is the incoming interface. Therefore, The message always has a direction, including that every time we calculate the cost, there is a direction along the way. This message passes through these interfaces. But for us, we will only count received ports. It is a cumulative value. For message 1, it receives from its own interface. Received a 0. But it has to add its own. Then it is 1 away from the root bridge. Further down there are other equipment. It sends out 1. Its own interface is 1 plus 1. It is 2 away from the root bridge. Okay. You need to understand these parameters. Because wait, we're going to compare them. Then we officially start talking about some other election content. Before we compare these 4 parameters, I want to emphasize. If STP is to conduct roll election, our first step should be to choose the root. An environment region must be the most important. Like a tree, the roots are the most important. So let's choose the root bridge first. That is, the order of our election is root first. After selecting the root, select the root port. After selecting the root port, select the designated port. Then the rest. Not a designated port. Also those ports that are not root ports will be blocked automatically. That is to say, I will not allow this interface to forward business traffic. Actually, the core concept of STP is to block ports. But STP does not just randomly pick a port and block it. It has to calculate first. After the calculation, the roll is determined. The last remaining ports are blocked. So this is a core idea of STP. What is the root? What is a designated port? Let's talk slowly. First we have to choose the root bridge. This is the first step. So how to choose a root bridge? I just said. All elections will be based on the packets sent by the device. Then the first step is when we conduct elections. Everyone must first know. The equipment on the second floor is actually incompatible with each other. For us, each switch only needs to start STP. It will consider itself the root. When you reach the NP stage, you will learn the specific packets of OSPF. Everyone knows that. Many agreements in the third layer are relatively modest. They don't think they have roles. But in STP they all think they are the root. It is now about to send a message to the outside world. Which parameter in the sent message will be filled with itself? Since it considers itself root, it will send out BPTU packets. Then this will fill it in. They start exchanging messages with each other. But the message exchanged between them is not called a loop. We will learn a lot of protocols in the future. In the protocol, various devices exchange messages with each other. They are not generated loops. The loop generally refers to the when a data is sent. This is a user's business data. It's a pretty standard ring. Now in this network, if passed like this is called a loop. However, the packets exchanged between devices are limited. Especially when the devices are all released at the beginning. The process is limited. And soon the interaction is over. This is not called a loop. They have to think of themselves as a bridge. Both fill themselves. The device thinks it is rooted. Will the devices all receive messages from each other? That is, prove that device A, device B, and device C can receive messages from other devices. They are interconnected 2 by 2. Then after receiving, they compare some parameters to determine who is the root. We will first compare the bridge ID of the root. So what does this parameter consist of? It must identify the ID number of the device inside. That is, it identifies its identity. So what is its composition? It is prioritized by 16 bits. Backplane MAC with 48-bit switch. Now many switches have no MAC address under the interface. In the early days, there were MACs under the switch interface. Each manufacturer is different. But now the second layer switch basically only has one backplane MAC. There is no MAC under the interface. That is to say, now this device has a MAC address. Then it will first use this MAC address, plus its current priority. Then to compare. This priority has a default value of. The default is 32768. Many parameters in the second layer default to this value. Everyone can understand. We can manually configure. I tell you this. If now there are 3 devices, the priority and the bridge ID of each device, all are by default. Then the MAC of the switch will start to compare. Among them, the smaller the MAC address, the better. So, first select the root bridge and compare the bridge ID. The smaller the parameter, the better. If we compare the priorities when we compare the results, we don't need to care about the MAC of the switch behind. So we are often in reality. The priority will be modified manually. That is, we can reduce some of the priorities. We do recommend that you manually specify the root bridge in the online network. Prevent misconnection and root grabbing. Because the root bridge is preemptible. You will learn some protection of BPTU in NP in the future. Then you will know the content. I give a simple example. Now there is a switch plugged in. If the priority of the device is all 32768. No modification. Originally it was the root. If it is connected now its priority. For example, it is 4096. Then it will take away the position of the original root bridge. It is no longer root. The location of the root bridge is taken away. Which means that the entire network topology will change. You should know. After the entire network topology is stable, BPDU packets will only be sent by the root bridge. Originally, the topology we maintain is that it is the root. Suddenly a device came in. It took the place of the root. Then the topology as a whole will change. Including what each device thinks is root has changed. It will have a considerable part of the time. It will bring some corresponding problems to the business. This is a matter of root priority. So we manually lower the priority of what you want it to be. The root bridge can be specified as 0. In the whole environment, we usually change to first set a 0 and set another 4096. You may find it strange. The priority must be configured as a multiple of 4096. So say the minimum value is 0. The second smallest value is 4096. When we configure a root bridge for it. Then configure a backup root bridge for it. The backup root bridge is when one day the root with priority 0 has a problem. Then the priority is 4096 to become the root. Generally speaking, suppose there are multiple devices in the environment. For example, this device performs best. I give it a configuration priority of 0. This device is the next best. I configure it to 4096. The two devices are 32768. By default, the first round of election compares the priority. We don't look at the MAC address. Compare priority. It sure is the best. Then it is the root. If it's gone, then it is the root. Not so performant, these devices will never be rooted. Certainly. If it's gone, then there's no way. We usually have to change equipment. It's enough for everyone to know this. Then we're done choosing the root bridge. There will only be one root bridge. Do you think there may be 2 root bridges? Some students may ask. Will these parameters not compare? It won't. Because we learned before. MAC address is globally unique. MAC address will not be repeated. So we must be able to compare. So there is no doubt that the parameters of the root bridge comparison are simple. Just these two parameters. A comparison will come out the result. In addition, we manually changed the switch backplane MAC to the same. Reboot next time. MAC address changed back again. It cannot be permanently modified. The MAC address is used as a hardware address and physical address of the device. It cannot be permanently modified. Everyone should know this. It is a physical address engraved in the chip of the network card. We also call it the hardware address. You can't configure fundamentally modifying the hardware of the device. This is the same as the bandwidth we changed before. A 10 megabit interface. A 100 M interface. You change it to gigabit. It's not a gigabit interface either. Physical parameters cannot be permanently modified. This is the first step. Let's move on to the second step. We are about to start the election of the root port. First note. The root port is to be selected on non-root devices. That is, there is no root port on the root bridge. All ports on the root bridge are designated ports. And you have to choose the root port on the non-root device. What port to choose as the root port? You need a measure. In all ports on non-rooted devices, we want to choose a port closest to the root. We also want to compare several parameters. There are 4 parameters to compare. The root port is actually the machine is connected to the nearest port of the root bridge. Only one root port on each switch. Except for the root bridge. Each device has one and only one root port. Let me draw a picture. I first draw 3 devices. I label them. This is device A. This is device B. This is device C. They are connected to each other. After the connection is complete, we're going to start the election now. Assuming the root has been chosen. Root is device A. We manually set its priority to 0. It is root now. No doubt. Between 2 other devices. Carry out some other port role elections. Now nothing more than. There is no root port on device A. Instead of having one and only one root port on the root device. That is. There is a root port between device B and device C. There are only 2 ports on device B. There are only 2 ports on device C. Both device B and device C need to receive data from their own 2 ports. Choose a port to be the root port. That is, these 2 ports in device B. One must be the root port. There must be a root port in device C. We will compare parameters. First let's compare the first parameter. It is called the root path cost in the inbound direction. This value is what we call RPC. Is the root path cost. We're going to compare. The smaller the comparison value, the better. When we compare, no matter what role is elected, all parameters are all smaller values are better. The comparison of almost all parameters in the second layer is that the smaller the better. In almost all 3 layers, the bigger the better. For us now, let's look at device B. Compared with device C, it is actually the same. Let me identify the interfaces of these devices. For example, this is the B1 interface on the left. This is the B2 interface on the right. Then the device C interface here. This is the C1 interface. This is the C2 interface. We are now going to select an interface in B1 and B2. Become a root port on device B. When we compare, in fact, it compares the cost of the root path in the inbound direction. The root will send messages to the outside world, which is then forwarded by the non-rooted device. That is, device A only needs to become the root bridge. All future BPDU messages will be sent by this device. Device B will receive such a message from the interface B1. The inbound direction refers to the inbound direction of the BPDU packet. If received from B2 interface, that's how the message came. What we are comparing now is the root path cost in the inbound direction. Then, for B1, its overhead is the overhead of this interface. For B2, its cost is B2 plus C2. That is, on device B, when comparing two interfaces, actually received by this B1 interface, assuming each counts as 1 first, we just calculate as an example. Because the default is the same. It is 1. 2 on the right. What we compare is the root path cost in the inbound direction. Then here comes a message. Only through one interface. Is 1. We calculated this when we calculated EIGRP before. The truth is the same. When packets come in, there are two interfaces. This is 2. If device B above, the RPC of the B1 interface is 1. B2 interface RPC is 2. We take a smaller value. Then this interface is good. The B1 interface is selected as the root port. But I want to ask, is it possible that I did the comparison and it didn't come out? Will there be such a situation? Okay. There is such a possibility. Some students may think, it seems like it should all be consistent by default. Let's draw a new picture. I now draw one more device. It is easier to compare, even if all its parameters are default. You will find it will also have some problems. I connect them. Now that's 4 devices. Let's say this is device A. This is device B. This is device C. This is device D. Suppose device A is still root. Device A needs to periodically send messages to the outside world. So where do we choose the port on this device now? We choose on this device. When device D makes a selection, which of the interfaces on the top and the left will become the root port? Let's take a look at a path it takes when forwarding. Device A now sends BPDU messages to the outside world from both interfaces. This message is sent to device B here. Send from device B to device D. Arrived at the interface of device D. Same. The packet sent by device A passes through device C. Also sent to device D. So now when device D is comparing the cost of the root path, how should the two interfaces be compared? It is now compared to this interface plus this interface. Assuming the default is 1. It is 2. Then received from the left interface. It is from the interface of device C plus the interface of device D. This is also 2. You will find, if we only compare the cost of the root path, it may not be comparable. That is, the root path cost received by device D from the two interfaces is 2. If this is the case, we will definitely not be able to compare. We will have a second parameter. The second parameter compares the bit of the upstream device. That is, forward bridge ID. The uplink device is the device that sends this message to you. For example, device B sends a message to device D. Device C sends a message to device D. Both device B and device C are called uplink devices of device D. If the RPC can't compare now, I will compare the bridge ID of the upstream device. In fact, the comparison is their priority plus MAC address. Is it possible that the bit of the upstream device is the same? Can you draw such a topology in your mind? In our picture, it is inconsistent. So if a picture like this In fact, it can be compared. But the reality is often not so easy. We have other possibilities. It's just that I can't compare RPC now. The bridge ID of the upstream device still cannot be compared. What's going on? I'll draw another picture to explain. For example, we only have two devices right now. I'll make a redundant circuit for it. I want to run two wires between two switches. The above is the root. This is 001. This is 002. So now let's compare. Suppose the following is device A. I choose the root port for device A. Let's first compare the root path cost in the inbound direction. The default is 1. Can't compare. Okay. Then compare the bridge ID of the upstream device. Now I found that the uplink device is only this one. If there is only one upstream device, then there is no way to compare. But we still have the port of the above device for comparison. Now although the upper equipment is the same, the device bid is the same as, but there are always differences on the device. For example, the two interfaces of the device are different. Then I just said, for PID itself is the priority of the interface. Of course it is also equal by default. But the port numbers are inconsistent. So I will now do a third comparison. The third comparison is the PID of the interface of the forwarding bridge of the peer device. That is, the PID of the interface of the uplink device. Let's call it the peer device. Because in this case, it must be that device on the opposite side. We'll do a comparison like this. Also, the smaller the better. So now in this picture, we definitely chose it. So now let's walk through the process. If so, the graph. We compare the first parameter and compare it. We choose it. If we compare it can't compare, we apply such a graph. We compare the second parameter. For example, if the value of device B is small, we choose B. This is the third picture. If this happens now, we choose it. Let me ask now. Is it possible that after comparing the interfaces of the opposite end, we still can't compare them? That is, I have now compared all three parameters. Inbound RPC, bid of the upstream device, PID of the peer device. But I still can't compare. Is there any possibility of this happening? Most people think it's impossible. Then I will draw a picture to explain. This is the root. There is a device like this in the middle of the root. I told you before. A hub is connected in the middle. Draw another device below. I connect them to each other. The above device is root. I now choose a root port for the device A below. We still compare parameters one by one. Every time we compare, have to start over. Make sure the first three are incomparable. First, the cost of the root path in the inbound direction is 1. Because the hub is not considered a device, so can't compare. Next, compare the bridge ID of the upstream device. Because the hub is a physical layer product, it's not a device at all. You can understand it as similar to a network cable. Its forwarding principle is very mechanical. No computing power. So it will not run any protocol. So actually the bridge ID of the uplink device now, or its bridge ID, can't compare. Then compare the PID of the peer interface. It's just an interface. The interface is incomparable. So what can be compared now? There is only one difference. If this can't be compared, then there's no way. Okay. The PID of the device's own interface is now the last parameter. Its two interface names cannot be the same. Priority is consistent by default. But the PID of the interface is inconsistent. So we will now compare. The PID interface priority is a 4-bit interface priority. 4 digits are 40101. The port number is a total of 12 characters. But this depends on each manufacturer. There will be some minor changes. Usually 1 this port, 2 this port. It is based on the port number. So 1 must be smaller than 2. So in this case it chooses 1. We now compare to this step. Is it possible that there is still no comparison? The future is when we troubleshoot every day. You will find that some may have been plugged in wrong. But we won't discuss these special cases when we study. Theoretically, as long as the topology we build is complete, as long as the wiring is connected correctly, then we must have a final result. So the election of the root port ends here. Compare these 4 parameters. If one of the parameters can be compared, stopped immediately. If you can't compare, we'll compare until the last parameter. In the end, I can definitely choose. The 4-bit priority also has a default value of, if I remember correctly, the default is 128. This will not be modified. Usually, we will not manually modify the priority of the port to make it the root port. This is the second step to elect the root port. According to the election root port, suppose we have now selected. You will find this is also what we choose in our courseware. If the parameters are not adjusted, definitely these 2 interfaces. It has an R written on it. R means this is a root port. It is this port closest to the root on each device. This interface is definitely closer to the root than it is. So these 2 are the root. Then after selecting the root, let's review. Here is a summary. When a non-root switch elects a root port, according to root path cost, peer bridge ID, peer PID, and local PID. These are the 4 parameters we just talked about. Okay. The root port is selected. Next we will start to elect the designated port. It also compares. The root port is called RP. The designated port also has its own name. It's called DP. For root bridge. All ports on the root bridge are designated ports. There is another sentence. There can be only one designated port on each collision domain. Remember what is called a collision domain? Look at this picture now. Device B and device C are in a collision domain. Each interface of the switch is a collision domain. Then the link between device B and device C. Actually under a collision domain. It is equivalent to the hub we just drew. The same is true for the hub. For the whole environment. This is a conflict domain. All hub interfaces are forwarding data. The overall scope of work of the hub is a conflict domain. I told you about the development history of the switch before. Hub. Bridge. Switch. A switch is a high-order bridge. I said that this is a big conflict domain in the hub. The best improvement made by the switch is an interface is a collision domain. So for us now, this is a conflict domain. But for hub networking, there's actually a big collision domain in the middle. That is, in this environment, we are connected through the hub. This is a conflict domain. So now under this collision domain, it has been selected as root. There can be only one designated port between them. By default, it must be a designated port, because it is a port above the root. Then in this picture, this port is naturally blocked, because the designated port under this conflict domain has been selected. So it gets blocked. But we generally don't talk about this special case. We generally speak according to the most regular, because we will see more such topologies in the future. So we follow it. We have now elected the two interfaces. These are the two root ports. These two ports are designated ports. We are now going to be on the link between device B and device C. Elect a designated port. Because each collision domain, there can only be one designated port. So there can only be one of them. So how do they compare? First we will compare the first parameter. Compare the cost of this machine. This cost is still the root path cost. But this time it is not comparing. All interfaces on the device are compared together. It compares to the cost of the root path closest to the root on this device now. I will give you an example. When we compared, the comparison is a single device root. Is a comparison between two ports. But now it is still relatively close to the root. But the compared parameter is the machine closest to the root. Then device B is the closest to the root. Is the distance from this port to this port. So we still calculate the cost like this. It is 1. If the root sends a message to device C in the future. In fact it is also 1. It's like two classes. In each class of B and C, the class leader will be elected first. This squad leader is the closest to root. They each chose 2. But when one day the whole grade has to choose an excellent class. Because the class selected to win, its port can become a designated port. The peer port is blocked. So now from the competition among the classmates in the original class, turned into a competition between two classes. If during this process device B wins, then its interface will become the designated port. It's not particularly appropriate for me to give this example. But you can understand. That is, the device is now closest to the root. This is 1. This is also 1. Like this. Actually we don't have to choose. But for this picture, it is selective. You will find it can't be compared in this picture. When the first parameter cannot be compared, we're going to do a second parameter comparison. We still have to compare two devices. If the cost of the machine cannot be compared, we will compare the bridge ID of our own device. We'll still compare priority plus backplane MAC address. Or the smaller the better. Assume that the MAC address of device B in this figure is smaller. Then this interface will become the designated port. This port will be blocked. It will no longer forward business traffic. Let's first look at if it is like this. How does the data flow in this diagram go? If once it is blocked, it's like all the characters have been chosen. This topology can start forwarding traffic. For example, there is a data sent to switch A here. It will send to switch B. It can also send to switch C. For example, this is a host. Whatever is going to some host behind device B. Or some hosts behind device C. It can reach. So it has no loops in the network. Include this device B. Even if you send a broadcast message, flooding through other interfaces of the switch. Reach the two interfaces. Flooding on other interfaces of the switch. Here is also the flooding of other interfaces of the switch. But for this link, in fact, we did not forward the data. So, this interface will not flooding. Then come back. And then sent back into the loop. It won't be like this. We're not looking at other devices now. These three switches reach other devices. Is a loopless path. Device B now goes to device A like this. The only way to go from device B to device C. This is how device A goes to device B and device C. If device C wants to go to device B, it can only go like this. It has no second choice. Then if this route is down in the future, the link between device A and device B is gone. If it's down, In the future this link will forward. So now if device A goes to device B, it can go to device C. If device B goes to device A, it can also go to device C. So it is equivalent to our daily situation. One link works. One blocked. When there is a problem with the link in the future, this link is up again. Guaranteed that now a device reaches each node. There is only one way to go. So it will never affect business traffic forwarding. Okay. Let's go on to compare. For this picture, since B and C are two devices, therefore, comparing bid will definitely be able to compare. But it is also possible that after comparing your own bid, you still cannot compare. I'll draw it here. For example, now the top device is still rooted. Now down here I draw more equipment. Let's talk about a slightly more complicated. This is a root. A device is connected below. Then there is another device below. Further down there is another device. I draw a few more. Here is a line connecting. Here are two lines. Then this is another line. But the difference is, the third device is a hub. I'll mark it now. This is device A. This is device B. This is device C. 3 devices. I now want to select the designated port on these two interfaces. Let's analyze the port first. Are there any ports that we can determine by looking at the picture? First of all, the port above the root must be a designated port. Secondly, device C has only one port. Each device has one and only one root port. Then it must be a root port. We are going to select the root port on device B. For device B, this must be the root port, because each device has one and only one root port. In fact, this port must be the closest to the root bridge, because they are directly connected. If this is the case, we don't really need to compare, because it is directly connected to the root bridge. So this is the root. So actually what we're going to choose is these two. We need to choose a designated port from these two ports, because this is a big collision domain. Of the two of them, only one can forward. If both interfaces of both devices forward, it becomes a ring. If you send a broadcast packet it becomes like this. Because the hub is unlimited forwarding for broadcasting. Device B has a broadcast packet coming out of here. Hub will forward. The switch forwards. Hub forwarded again. Then they will form a circle. So only one of them must work. Let's compare now. First compare the cost value of the machine. This has been compared. But they are consistent between the two. Next compare the bridge ID of the device itself. This is a device. Both are device B. You can only compare the two interfaces of your own device. That is. Finally we compare the PID of the device itself. Therefore, it is impossible for us to compare to this step. So far you will find, if an interface, it is neither root port, nor specified port, then now it will automatically become a blocking port. So as the whole STP protocol, the reality of the election in STP is more by blocking the port to complete the final effect of the entire protocol. But after all the identities of all ports are determined, you can elect the last blocked port. This is also the last core content of the STP protocol. So let's do a recap. Choose the root bridge first. If you choose the root bridge, compare each device and you will be able to choose it. Second, choose the root port. The root port has 4 election parameters. Until one is compared. Comparing to the 4th one can definitely compare. Each device will have one and only one root port. Then select the specified port. Designated ports on the root bridge. And there is only one designated port under each conflict domain. After we have selected all the above roles. If a port is neither root nor designated port, then it will automatically block. Okay. Let's move on. It will have a port state. When we talked about STP just now. Port role. Port roles are just one of the mechanisms in STP. Another mechanism of STP is called port status. Let me introduce you. For example, as such a device. Suppose we choose it to be a designated port. Assuming the port is blocked. Now it's a blocking port. Blocking the port means, if the entire environment topology is now, the link between C and D is down, then I'm doing data forwarding. Actually only these 3 lines are available. No matter how you retweet. No matter what message is sent. For example, a PC accesses an address on the same network segment. Also send ARP broadcast. If this line is connected with broadcast packets, come in from this interface. Retweet like this. It is a ring. But now because of STP, we can block this link. So this broadcast packet can only be like this. So it won't have a ring. STP can do this. Then, as we just said, actually, you can think of ARP as a user traffic. Because ARP is what you need to request. For example, you want to connect a PC from device A. Access a PC connected to device D. C to request D's MAC. This is called business data flow. Under normal circumstances, these links of communication are forwarded traffic of running users. Certainly, our daily STP protocol packets are also running here. But it is to maintain this agreement. It doesn't count as user traffic. Then I have a question. When I manually change the priority of D to 0 now, I want it to be a root bridge. Then once this becomes the root bridge, please pay attention. Originally, device D will always receive the message sent by device A. It will also receive STP messages from here. The blocked port we are talking about is blocked. It just doesn't forward traffic. But it will receive STP messages. In the sent BPDU message, there will always be a parameter filled with the root ID. If at a certain moment I manually set the priority to 0, then, for the device, it is receiving the incoming message. It knows that the parameters of device A are not as good as it. I just told you. The root bridge is preemptible. Let's compare the root bridge first. The comparison is the bridge ID. It finds itself better. Because I am smaller. Priority is 0. Then it becomes the root. Then if it becomes root now, then the port on the root is the designated port. Designated ports can forward data traffic. Then it can now send messages to the outside world. Equivalent to both interfaces are activated. But you need to know one thing. When you finish manually tuning now, this command takes effect immediately after entering. The device knows it is rooted. Both interfaces forward immediately. Device A is now a root. Does it know that device D is now forwarding data? Because A is originally the root. Its 2 interfaces are also forwarding. D is also root now. It also forwards. A also forwards. This is a short loop. It's like a class. It turned out that this was the monitor of the class. One day the teacher directly appointed D to be the monitor. As a monitor, I have my own job every day. Then now there are 2 monitors. It's embarrassing. Serious for the environment. Device A now all ports work. Device C all ports work. All ports of device B are also working. Originally, this interface of device D worked. But this interface is not working. Certainly. Device C itself will not forward traffic, because the whole link is broken. But at a certain moment, once everyone starts working, this is a circle. Because after device D becomes the root port. Do you remember what I said earlier? I said that when the topology is stable, only the root bridge will send BPDUs to the outside world. Other devices just forward. It is the originating BPDUs. It also sends out. It will carry its own bid. When the equipment along the way is received, they will find that there is a better. It just knows that the role election is now going to be rerun. But this message, from this device to other devices, let others know that it is stronger and better. Let others know that it is now root. It takes time. This role can be switched instantly. But the port cannot immediately forward business traffic. Otherwise it will still have loops. So for STP, state switching is something that can be done in an instant. But the forwarding state cannot be switched. That is, the role can be switched first. But the forwarding state cannot be switched immediately. Need to wait a while for data forwarding. So, it is not that. The port role switch will forward the data instantaneously. Whether the forwarded data can be forwarded depends on another thing. What we just talked about is called the port role. What we are discussing now is called the port state. There are 5 states. You don't need to pay attention to these lines. First, there is a thing called disabled. Under what circumstances will a port role be disabled? First, this port does not use STP. It's just that the STP function is not enabled. This feature is enabled by default. That is to say, you turned off this function in the interface. Then this port does not participate in the calculation of the overall STP. Then it is disabled. Or the port itself is down. No job. Not turned on. Then it does not process BPDU messages. It is also disabled. It will not process BPDUs in this state, because BPDU belongs to a message in STP. This protocol is not currently running. Then this message cannot be received. In this state, you cannot forward traffic. This is the first state we're talking about. Let's look down. There is a blocking. This is what being a blocked port will end up in. It has some characteristics in this state. It will receive and process BPDU messages locally. As we just said, between 3 devices. Assume that the interface in the middle is blocked now. It also receives messages. That is, we will still send messages like this. The device still transmits from this interface. It will receive. Same goes for this. It will also send. This interface also accepts. So this line can forward STP packets. Just don't forward user traffic. Because this is only logically blocked by it. Do not forward traffic. But STP messages can be sent and received. Because this interface is not really down. And it will not learn the MAC address. It's just a pending state. Is a blocking state. It is the final state of the blocked port, called blocking. After booting, this port automatically has STP. Will soon become blocking. Let's go on. This has a state called listening. It is characterized by. It will not learn the MAC address. But it will start the calculation of STP. Including this interface can send and receive BPDU. That is, the blocking interface only receives, but won't send. Listening can receive and send BPDU messages, but it doesn't count MAC. Then learning. It is to receive and send BPDU messages, and also learn MAC address. And will build the MAC address table. Don't forget what you learned. Many devices are connected to the switch. This is interface 1 and interface 2 of the switch. BPDU messages also come in from the interface. I learned the source MAC. So what I learned is the MAC of the switch. Switches run on each other. It will first learn the MAC of the switch. It also has a backplane MAC. We will use the message of the switch. STP will use its own backplane MAC. Carry out two-layer encapsulation. So it will learn MAC. There is no essential difference between the two. You should learn fast STP and multi-instance STP in NP in the future. Especially in fast STP. These two states are actually combined into one. It does not need these two states. In fact, this is the design in STP. I personally feel redundant. It does not actually need to be designed as two. In fact, the biggest thing they have in common is the same. It is to receive and send BPDU. But they do not forward traffic. But there is one thing that needs your attention. We switch from disabled to blocking. This state is happening soon. As long as this interface is opened. And run STP. Soon became such a state. Then switch from blocking to listening state. In fact, it can be switched over quickly. But from listening to learning, it takes 15 seconds. This is called forwarding delay. Also called timer timeout. Our true forwarding state. Called forwarding. It is a forwarding state. From learning to forwarding state. It also takes 15 seconds. Only when this state is reached can the user traffic be forwarded normally. This state is also the final state of the DP port and the RP port. So like the picture I just drew for you. Originally a left port is blocking. Now manually designate that device as the root bridge. Its two original blocking ports will become a designated port. Do not forward traffic from blocked state. Forward traffic to the end. It needs a countdown in the middle. That is, in the process. It takes 15 seconds to read. It's instant. So since you designated it as the root bridge, until it actually forwards, takes 30 seconds. These 30 seconds are for. Make sure that the entire network can receive this message now. For example, now the message has to be forwarded all the time. We have relatively few devices in this picture. You sometimes run into situations where you have a dozen switches. This message has to be forwarded one by one. In the end, it will not work until all the devices on the entire network know that the route has changed. So you have to allow plenty of time. Let the whole network recalculate the topology. Because these two interfaces are now in the forwarding state. Other interfaces need to be recalculated. Then one can imagine. If I recalculate. These two are designated ports. These two must be root ports. One of these two must be the root port. One is blocking port. You should know. BPDU messages are sent out from the specified port. On device D is the designated port. It sends out. The root port of device B receives this message. Then the designated port of device B sends this message out. So actually, BPDU messages are always sent from the specified port. You don't need to memorize this concept. You can understand it by observing the phenomenon. This is called forwarding delay. Also called timeout. Let's take a look at the contents of the courseware. In fact, this is called a transition diagram of a state. But actually it's not very useful. Port initialization or enable. Once the reboot is started, STP runs by default. It will become blocking. Then we will start the election of the port role. Select root port and designated port. Then this state is determined. Role has been determined. It is now a root. Already a designated port. It is forwardable. So now switch to these two states again. Actually just waiting. No need to calculate. It writes a 3 here. It means if a port is no longer the root port or designated port, it will become blocking. Suppose there are 4 devices. Originally, the 2 interfaces of R1 were designated ports. But it received a message from this device. It is now manually assigned as root. Then these 2 are designated ports. One of the ports is about to be blocked. Originally one port could be a designated port, forwarding in forwarding state. But now suddenly it is no longer the designated port. Becomes a blocked port. It becomes blocking. And if in the process of all interface state transitions, it is no longer root, or manually adjusted, its state toggle also goes back. You will find it's a simple matter of a moment to go back. Let's take a look. For now, if you want to go from blocking to forwarding, you can only go this way. Wait here for 15 seconds. Wait here for 15 seconds. Wait here for 30 seconds. But you switch from forwarding to blocking instantly. There is a word here called forward delay. It's called a timer timeout. Overall roll convergence of STP. All roll calculations are based on forward delay. It is equivalent to the concept of reading a table. Switch when the seconds are enough. Switch all the way to the final state to complete the forwarding. Let's make a brief summary. After the final topology is stable, there will only be 2 states. A blocking, a forwarding. All ports are forwarding as long as they are root ports and designated ports. The blocking port is blocking. There will only be these 2 states. These 2 states are actually overused, so they are not very important. When you learn other STPs in the future, you will find that it will make some changes. Like the states in between. It actually doesn't need to define so many. Doesn't make much sense. Okay. Let's go on. In fact, we have said about BPDU. But there are a few parameters in it that we haven't mentioned yet. These 4 more important parameters have actually been mentioned by us. I briefly introduce other parameters. PID is called Protocol ID. This is the ID number of the STP protocol. It is fixed at a value of 0. PVI refers to some other STPs that you will learn in the future. For example, STP here is 0. RSTP is 2. MSTP is 3. The values here are different. That is, identify the specific type of STP. There are 2 types of BPDU types. One is called config BPDU. The message you are seeing now, it is a configuration BPDU. Is in the form of config. We'll get to another BPDU in a minute, called TCN BPDU. It's just these 2. So it identifies the type of BPDU message. Next is the flags. It's hard to explain this to everyone at this stage. Inside it is assigned bit 1 by 1. The difficulty of STP is here. We have learned something called 5K before. In EIGRP, we calculate the metric based on this. It's like 5 switches. For example, it chooses 1, 2, 3, 4, 5. Then 5 digits. Each digit has 2 values of 0 and 1. 0 means no reference. 1 for reference. So the same is true for flags. It will also have a lot of parameters. A total of 8 parameters. We know 2 at this stage. One is called TC. One is called TCA. We will talk about it later when we talk about TCN. You need to know that it belongs to the 2 flags and flags. Let's go on. The middle ones have spoken. We say that the following parameters. First look at the message age. It is called a message sent by the root bridge. total time to reach this switch. You can understand it like this. It actually refers to the age of your message. When the root bridge sends a data, the message age in the message originating from the root bridge is 0. Increment by 1 each time a device is passed. Now you see it receives 0. Assuming there are other devices behind it. When it forwards, we'll fill this value with 1. Then send out. Then it receives 1. The next device received is 2. That is, indicates when the message is delivered to the device now. How many devices have gone? It will increase by 1 each time it is issued. Its current distance from the root. For a message. If this value exceeds 20, then the message will be discarded. So usually when we network, will there be 20 devices that keep forwarding in this way? We usually only have a dozen. If longer, the whole topology is relatively less reliable. To us, this value can be modified. Change on max age. For example, the default here is 20. So at 20 it drops. If you change this to 30, then the message age will be lost if it exceeds 30. So when receiving and sending messages, for example here is 20. It received is 13. This device will directly compare these two parameters. As long as it is less than the latter parameter, we'll continue to send down. If they are both equal then no. We call it the aging of BPDU packets. The technical term is too large a network diameter. There are too many devices in the middle. Cause the root bridge connection to fail. That is, it's now unreliable from root bridge. It may think it is now disconnected from root. Let's look down at hello time. This hello time is different from the hello time in OSPF. It is 2 seconds. It means that the root bridge will send a configuration BBDU to the outside world every 2 seconds. It is now telling the whole network that it is the root. It is to ensure the stability of the network topology. Just like hello packets greet each other. This root bridge must keep growing. The device below will forward. When the topology is stable, only the root will send BPDU messages. Other devices only forward BPDU messages. If the STP protocol depends on the mechanism of the overall protocol, keep topology stable, then there must be a strong association. Just like OSPF sends hello packets to each other. You want to make sure that the current network topology is stable. It is necessary to send a message to the outside world every 2 seconds. All devices forward all the time. To make sure the uplink device is still there. Determine the construction of the overall network topology. The last one is called forward delay. This is its parameter. It is also modifiable. But usually no one changes. Because STP is no longer a separate protocol. Usually it will be combined with some other protocols. For example, what we use more now is actually link aggregation plus stacking. STP is just a protocol running on the bottom layer. Slightly medium and large networks will not run STP alone, because it's too slow. Let's take a look at max age and message age. Now as the root, its BPDU message is sent every 2 seconds. The message age sent is 0. Max age is 20. Hereafter, it will be 1 when it is sent again. This is the next device. Reissue is 2. If it keeps going down. Sent to a device. It was 20 when it was received. It will be 21 when it goes out. Then the device below will discard the message. It's gone. So, if the current message age is greater than max age, non-root devices will discard the configuration BPDU. Okay. Let's talk about the type of failure next. Let's take a look at how quickly it completes the switch. First of all, as a root bridge, if there is a problem with the root once, then it will not send BPDU to the outside world. If the root bridge fails in the future, then the blocked line will be reopened. Both of them have to be re-elected. The selection rules are still the same. Let's look down. There is a direct link failure here. A means to block the port. This port is also blocked. Equivalent to this topology and now blocking two interfaces. Originally this line was forwarded. If the interface is down now, then it is directly connected to this device. Whether it is this interface down, or this interface is down, it will immediately turn the standby port into the root port. For this device, originally it was the root. But if it goes down, another interface will become the root. Because each device must have a root port, and is closest to the root. It is 1. If go down, this is 2. So even if the RP is broken now, when we choose, still choose it. But please be careful. It transitions to a root port state instantaneously, because it can detect the failure of the direct link in an instant. But after turning into the root port, when it arrives from listening to learning, it waits 15 seconds. From learning to forward state, wait 15 seconds. So although the status can be switched instantaneously, but this link can be used after 30 seconds. So this is a direct link. This is indirect. This graph is very complicated. Just understand it now. Don't need to know that much. The picture above. There is a direct connection between device B and device A. So once B is directly connected down now, it immediately knew there was a problem with the wiring. But not here. Now if there is a problem with device C, if device B is broken here now, then normally, device C should receive the BPDU message from here. And also received BPDU message from here. It will receive from both ends. But for us, if the end of device B is broken, that means device C will no longer receive BPDUs from this end. Because device A can't receive the data sent by device B. Device B will no longer forward to device A and device C. Then device B cannot receive. It will also have a 20-second wait. Same as max age. But it doesn't read like that. It is 20 seconds. That is, it is after a period of 10 BPDU messages. No more BPDUs are received from this interface. It knows that the network topology may change now. There may be a problem with device B. Same for device B. Device B has not received the BPDU message from device A for 20 seconds. It may now consider itself rooted again. This is more complicated. You will find. Here is a yellow BPDU. It will now take the initiative to send a BPDU to device A. Then fill in the root ID inside as yourself. It wants to tell device A that it is now rooted. However, since device A has always been connected from the upper interface, received a BPDU from the real root for it, it can be compared that the root parameters are better than device B. So device A will now also open its own port. Then send the corresponding BPDU message to device B. Tell B that there is still device A in the environment. Tell B it is not root. Afterwards, when device B receives a better configuration BPDU from device A, it will think that it is not the root now. Then it will put itself in this state. Switch to be a root port. Then for end response, it is a designated port. So for device A, first there is 20 seconds. No more messages will be received from device B. Secondly, it does not receive messages. It thinks that the topology has changed. Then there is no loop now. I'm about to upgrade my status. It was originally blocked. Now forwarding. Then we have to count down. Read to 15 seconds. So after 50 seconds, it will now send its own BPDU message to device B. Device B will reply to it after receiving it. Then the entire network topology is stable. So be sure to know. When device B fails to receive the message, it will consider itself rooted again. So there will be more time wasted here. For the whole STP, the fastest is 30 seconds to complete the overall recovery. Therefore, STP is not suitable for the overall forwarding speed of the current business. Because it's too slow. Recovery time too long.